Since its creation, the Earth has never stopped changing. Colossal forces have hurled ocean floors upwards and made them into towering mountain ranges. Incredible collisions have created entire continents. These tectonic forces are still at work today. We see them in volcanic eruptions, earthquakes, and tsunamis. Tectonics sculpt our landscapes, change our climates, dry up our oceans, and can destroy life. The tectonic history of Asia is staggering. The largest continent on Earth has been subject to volcanoes of such power that they caused the greatest die-off in the planet's history. The world's most violent tectonic collisions gave birth to our highest mountains. Today, the most densely populated continent could actually see one of its countries disappear under the waves. It's all part of the endless voyage of the continents. At its very beginning, the Earth was a burning ball of liquid matter. Any solid ground was constantly melting back into the Earth's fiery core. As the Earth gradually cooled, rafts of solid matter were formed, a process that took billions of years. In Russia, a team has set off on a journey back through time. They're searching for rocks that date from the birth of the Asian continent. Rocks that have had to survive the violent volcanic episodes of those days. There are no roads that lead to this remote location. To get there, geologist Dmitry Gladkuchev must sail across Lake Baikal, the Pearl of Siberia, the world's oldest and deepest lake. Lake Baikal is one of the shrines of Asian geology. The rocks found on its shores tell a 3 billion-year-old story, one that started soon after the birth of our planet.
We've come here to retrace the geological history of Siberia.
This is where the researchers found the zircon crystals that contain the record of Siberia's past.
Те породы, которые мы здесь обнаружили, мы получили по ним изотопные датировки.
Radiometric analysis of the isotopes indicated that the zircons found here are 3.4 billion years old.
Те, которые мы здесь наблюдаем, он составляет 3,4 миллиарда лет. Которые и принимали участие при формировании.
Deep within the zircons is evidence of the oldest rock formation in Siberia.
В это время 3,4 миллиарда.
What Dmitry has discovered right here in Siberia is a trace of the original Asian crust, rocks that were formed almost 3.5 billion years ago. But that's not the end of the story. This outcrop tells another tale, something that happened billions of years later.
Древние ядра цирконов.
Long after the oldest zircons were formed, this whole region underwent a remarkable transformation. That happened 1.9 billion years ago.
То есть в большинстве своем они переработаны более поздними процессами. На рубеже около.
These much younger rocks seem to have been welded onto the original formation. Asia was expanding. 2 billion years ago, only 30% of today's Asia exists on the surface of the Earth. But as the planet cools down, the Siberian mass grows, annexing more and more rafts of rock as they form. Soon, the entire Earth is covered by a thin crust. The heat coming from the Earth's core allows more molten rock to escape. This breaks the crust and splits it into tectonic plates. The continents are on the move. The results are cataclysmic. Mountain chains are formed. Earthquakes and volcanoes are everywhere. The Earth's great internal mechanism is in action. The continents come together and separate in a repeating cycle that continues for billions of years. At the heart of this great voyage, Lake Baikal is witness to one of the major tectonic collisions of Asia's long history. On the south shore of the lake, rocks tell us the story of how this colossal event unfolded.
This particular site is truly unique. The explanation of how plate tectonics formed modern Asia begins here. 500 million years ago, northern China traveled 2,000 kilometers to eventually collide with Siberia, closing up an ocean. I'm walking on a geological frontier that explains how Asia ended up the way it appears on our maps today.
In order to become the continents we know today, huge tectonic movements still had to occur. About 300 million years ago, all the continents are moving towards each other. Northern Europe collides with Siberia, and the two continents are welded together. That impact creates a 2,000-kilometer-long mountain chain, the Urals. From north to south, along the old mountain chain are tens of thousands of iron deposits, along with copper and other metals. These are the result of massive tectonic events and the violent chemical reactions that followed them. Before its collision with Europe, this was a chain of volcanic islands. A history that geologist Viktor Pushkov knows well.
Here, underground water, heated to 300 degrees Celsius, spewed out from the depths of the earth. The water was under very high pressure. Within the rock, it crystallized as what we call a column of black smoke. Over time, these sulfides turned into the mineral zinc, which we see all around us.
Black smoke became zinc, all thanks to the intense heat generated by the collision between Europe and Siberia. That zinc has been found in a number of mines to the west of the Urals, mines that are still the economic engine for the region. Soon, the supercontinent, Pangaea, brings all the continents together into a single mass, all except one, southern China. Asia's largest missing part drifts alone in the middle of the ancient Pacific Ocean. At this period, the biodiversity of the Earth is extraordinarily rich and varied. But a major upheaval is about to happen. In the northwest of Siberia, the crust splits open. 3 million cubic kilometers of burning lava spills over a surface the size of modern Europe. It is the largest volcanic event of all time. This cataclysm has an enormous impact on the environment, saturating the atmosphere with toxic gas and upsetting the chemical balance of the oceans. Oddly enough, it's in southern China, thousands of kilometers from Siberia, where scientists can find proof of that ancient volcanic explosion.
We came halfway around the world to see this, and unfortunately, there's nothing left to see. The outcrop we were looking for is right there, under those houses.
Paleontologist Sylvie Crasquin is investigating a rocky outcrop, the only one of its kind, hoping to trace the effects of that ancient Siberian volcanic event. She is looking for the dividing line between life and death, what geologists call the Permian-Trias boundary of 251 million years ago.
Wow, c'est génial!
Wow, that's great.
Les gros macrofossiles là qui ont été.
Look, we have these large macrofossils that were photographed in 2005.
Il y a des petits gastéropodes.
There are gastropods, lamellae branches, fossils that can be seen with the naked eye. We have fossils of about 1 centimeter in length preserved right on the surface.
C'est vraiment très très chouette.
We'll have to be careful not to hit them with our hammers. We'll work around them.
En dessous.
We can see this large discontinuity on the rock face. It shows the boundary between the Permian and Triassic eras. I've never seen it so clearly marked.
En fait, il y a très peu d'endroits dans le monde où on voit aussi
There are
bien.
very few places in the world where you can see the boundary so clearly. Here we can see the Permian segment where there are lots of fossils.
En fait, beaucoup de traces de fossiles, ce qui veut dire que
This means that during the Upper Permian era, there was an abundance of life.
de ces roches. Et au-dessus,
But afterwards, we don't see anything. All life has died out.
la vie a complètement disparu. Donc ce niveau
So this flat line here tells the story of a mass extinction of about 98% of marine life.
environ 98% des familles marines.
Sylvie's research proves that 250 million years ago, the massive volcanic event in Siberia was responsible for the greatest extinction in the history of the Earth. An extinction that spread even to southern China, which at the time was still separate from the rest of the continent. Sylvie Crasquin thinks that in fact this isolation may have played a major role in the preservation of life on Earth. As she climbs the rocky layers above the Permian-Trias boundary, Sylvie leaps ahead several million years in geological time. She is looking for traces of microorganisms that could have survived that ancient cataclysm. These fossilized ostracods, or seed shrimp, are only 1 millimeter in diameter. Yet many species on Earth today owe this tiny creature their very existence.
Ça nous laisse penser
Our research tells us that this whole region was some kind of refuge, the last environment where fauna may have survived, and then gone on to re-inhabit the entire
de la
planet.
planète.
By keeping China separate from Pangaea, tectonic forces miraculously preserved microorganisms that allowed life to start up again. As this repopulation takes place, Pangaea splits apart and continents start drifting away. To the southeast, small rafts of crust are wending their way towards Asia, eventually becoming Thailand, Cambodia, and Vietnam. But scientists are on a quest to find out just when these microcontinents welded onto Asia. Oddly enough, two paleontologists may hold the key to this geological mystery. Eric Buffeteau and Varavud Sutithorn have come to northern Thailand just outside the city of Callison to investigate a mysterious object found by a peasant working his land.
นะเจอมาจากที่ไหนอ่ะ
ทิศตะวันตก
ที่ของภูน้อย
ครับ
โอเค
ตะวันตก
It only takes a quick look for Eric to decide that what looks like an ordinary rock is actually the vertebra of a very large animal, perhaps even a dinosaur.
It's a big dinosaur, maybe 15 meters.
แล้วก็มีกระดูกอยู่เยอะไหม
ครับ
เยอะนะครับ
That's from the hill here.
From the hill here and
Which is-
he said it's a lot in this area so we shall go with him after this
ยังให้โยวัดก่อน
Eric and Varavud's painstaking work has been rewarded. More than 40 large dinosaur fragments have been patiently recovered. It's an overwhelming find.
this week
It's been an exciting week for us because this large dinosaur bone specimen looks a lot like a fossil that was found in China.
China
We will now be able to compare them.
between the Thai dinosaur and the Asian dinosaur
They may have the same origin.
that it from the same
This would
root
prove that the two
and
countries have been connected for a very long time.
connect together.
It's a very important discovery.
Very important.
Could it be that this dinosaur really migrated all the way from China? If that's the case, it could help scientists understand more about the movement of the continents. One of the fragments is particularly interesting, and researchers have decided to bring it to a nearby lab for analysis. A difficult operation. The fossil has to be plastered, just like a fractured bone. If not, it would have broken into tiny pieces as soon as it was unearthed. Eric and Varavud have in the past recovered bone matter from several species of dinosaurs,
แล้วก็ค่อยๆลดลง
but none can compare
ค่อยๆ
to this one.
ค่อยๆ
It must weigh around 200 kilograms. The first step is to establish the fossil's age and ancestry. Researchers have determined that this species is approximately 150 million years old. And most importantly, that it did not develop on the raft that would eventually become Thailand.
So it looks like our dinosaur is a Mamenchisaurus, very similar to the ones we found in China that date back to the same era, the end of the Jurassic, about 150 million years ago.
50 millions d'années environ.
Discovering and dating this dinosaur proves that Thailand was already attached to South Asia at least 150 million years ago. This type of finding allows researchers to continually update their maps of South Asia at the end of the Jurassic period. And it casts light on the colossal tectonic forces that could move continents. Soon after South Asia joined the continent, the reign of the dinosaurs reached its height. This has made some scientists wonder if the next stage in the formation of Asia played a decisive role in the extinction of these enormous reptiles. Far to the southwest, India breaks off from Africa and begins its voyage north. It moves in a kind of tectonic fast lane between the Australian and African plates and jams into South Asia at the record speed of 15 centimeters per year. This is the most significant tectonic collision in recent geological time. And India's voyage was not smooth sailing. In Mumbai, British volcanologist Mike Widdowson has come to work with his friend and colleague Sam Cessna. For the last 25 years, Mike has been trying to discover how India's tectonic journey may have killed off the dinosaurs. He is studying a unique tectonic phenomenon, the Deccan Traps. Sam and Mike have traveled on this road together dozens of times during their research. As they drive, they pass thousands of cubic kilometers of unique cliffs. Despite their appearance, these layers of rock were not formed like sediment on an ocean floor. They are the result of successive, gigantic lava flows that once covered almost half of India. There are staggering quantities of this lava, called basalt, throughout the country. Basalt is one of the best building materials. But the question remains, since there aren't any volcanoes near here, where did all the lava come from? To answer that question, we must go back about 70 million years. India is moving towards its modern position. On the way, it passes over a fixed and permanent hotspot in the Earth's crust. Under this spot, there is an enormous amount of magma. As India passes over, there is an upwelling of molten rock, called a plume by geologists. This melts the tectonic plate that supports the whole northwest of India. What happens on the surface is cataclysmic. Vast outpourings of lava pile up over thousands of square kilometers.
What we can imagine here is the first crust of the lava flow forming. Because more magma is being supplied into this lava flow, it starts to crack apart, it starts to fracture, and it's pumping and pumping and pumping, it starts to crack. And more of the magma starts to come up through the fracture. And what we have now is a large fissure beginning to develop with more magma coming up to form the next lava flow on top of this one.
Eruptions at the Deccan Traps went on for 5 million years. Some researchers believe that the huge amount of toxic gas that was released into the atmosphere had a global effect. And this is what killed off the dinosaurs. This theory contradicts the common hypothesis that the dinosaurs' disappearance was due to a gigantic meteorite that crashed into Mexico about 65 million years ago.
We have in front of us exposed probably the top third of the entire Deccan succession. From the valley down below at 100 meters to the top of the plateau, it's built up lava flow by lava flow by lava flow to a thickness of probably 3, even 4 kilometers.
The traps can be plainly seen these days due to 60 million years of erosion.
This might be a feeder dike, this might be one
Wind and rain wore the cliffs down so much that in certain places geologists can see a drop of more than 1,000 meters, an amazing view of the layers of lava.
Just here. So we've found a locality here where both geology and geomorphology collide.
Right.
This is a pretty unique location. That cliff there represents 1, 2, 3, 4, 5, 6 lava flows which came out so rapidly there was no soils developed in between, probably even welding themselves one on top of the other. What scenery though. Terrific place. These steep descents down the roads of the Western Ghats have a particular significance to me as a geologist. On these occasions, this car turns into a time machine. With every kilometre we pass, we strip off yet more and more lava flows and we go further and further back in time towards the time of the dinosaurs and beyond.
In the Deccan Traps, there is evidence of ancient life that appears between the layers of lava. One of them attracts Mike's attention. This band of clay may have been laid down at the same time that the dinosaurs became extinct.
This terrific exposure, which consists of a lava flow, a large lava flow, which came across this red material, encapsulates in many ways the kinds of environments which were existing during the Deccan lava succession. The red material upon which it sits, this red bowl, this soil horizon, probably took hundreds or even thousands of years to be created. But the really amazing thing about this is that a muddy pool, which this probably was, is the ideal site for growing plants. How do we reconcile the fact that we have plant growth, ecosystems existing at the same time that this eruption was supposedly changing the atmospheric composition? And that is one of the big questions that scientists are trying to get to grips with today.
Mike is hoping to discover if life could have survived between the layers of annihilating lava, and whether this life corresponded to the time of the dinosaurs' extinction.
To begin with, couldn't see any fossils at all in these, but the more we looked and the more we investigated, we started to find fossil organisms, little shelled organisms, and along with these we found pieces of bone. The difficulty always was in actually precisely dating these. The other thing we started to find in 1 or 2 locations was actually pieces of wood and even segments of tree trunks. So it was actually quite large trees, probably small forests in some areas, forested areas. We can actually set the laser going, melt the rock and get the gas out. And it's really exciting for me to try and find out just how old these rocks are.
Yeah, shall we start with this one here?
This one looks a good one. Just start turn the laser up now and away we go.
Okay.
I'm really looking forward to seeing what age this particular rock is going to give us.
The analysis reveals that samples taken from the clay layers are 65.5 million years old. Mike has found complex ecosystems that were formed between lava layers, and they date from precisely the time that the dinosaurs were wiped off the map. This throws doubt on the hypothesis that the extinction of the dinosaurs was caused only by the formation of the Deccan Traps. Perhaps the Mexican meteorite theory is correct, or maybe they both are.
Was it a meteorite or was it volcanism that killed the dinosaurs? And I think the work that we've done actually shows that that's a far too simple question. If you had a huge eruption like the Deccan, could it have pushed regional and global ecosystems to the brink of extinction? Then it might be no great surprise that if we had a major meteorite impact during that time, that it would send the whole system over the brink. In other words, we were at a tipping point, not only in the environmental systems which were operating on the Earth in the late Cretaceous, but also a tipping point in the history of life.
In India, the scars left by eruptions show how plate tectonics can influence the very course of planetary life. But the Indian plate's most spectacular adventure is yet to come, a transformation that will once again affect the entire planet. Propelled by the power of tectonics, India hurtles northward at 15 centimeters a year, a breakneck pace in geological terms. About 50 million years ago, it slams into the wall of South Asia. This collision gives birth to the most imposing mountain range in the world, the Himalayas. 14 peaks are over 8,000 meters high, crowned by the world's highest mountain, Everest.
That's how to do it.
Even for those who know the landscape, it is hard not to be impressed by the sheer power of our planet. Laurent Godin and Kyle Larson are Canadian geologists who have been studying how the Himalayas were formed. They're in Nepal to continue this research. Many mysteries remain to be solved here in the midst of these towering peaks. The Himalayas are the most colossal construction site on Earth. For our geologists, they represent a vast open-air laboratory. Their mission begins in Jomson, a tiny mountain village perched at 2,800 meters.
We've just walked into a little souvenir shop here in Jomson, and we've found ourselves an ammonite. And these ammonites are ancient squid-like creatures. And the spectacular thing is these once lived, depths around 3 kilometers or in oceans that deep. And now we find them 3 kilometers above the surface of the Earth in the middle of the Himalayas.
How did these sea creatures end up here, 1,000 kilometers from the ocean? To find out how an ocean floor ended up high in the Himalayas, Kyle and Laurent travel up to 4,000 meters above sea level.
Just grew in thickness. What we have here are rocks from the bottom of the ocean. These rocks were laid down completely horizontally, totally flat. As you can see in this outcrop, they're not flat anymore. In fact, they've been folded quite spectacularly. They've been compressed horizontally, they've been thickened vertically. So instead of being now 2 kilometers or something below the surface of the ocean, we're now more than 2 kilometers above the surface of the Earth, right in the middle of the Himalayas.
As it moves northward, India squeezes the ocean between it and Asia. The seabed crumples up and out of the water and takes a journey of several kilometers vertically, which is why there are marine fossils high in the mountains.
Just to think of the forces necessary to take these from the ocean floor way down below the surface of the ocean, flip them up on end and put them now in some of the highest peaks of the Himalaya. Just spectacular.
And now we find them 8 kilometers above sea level. Absolutely incredible.
Having obliterated the sea that separated it from Asia, India pushed itself under the Asian continent. By modern times, India had already lost 1/3 of its surface area. Geologists have long thought that this was the only way to explain the formation of the Himalayas. But Kyle and Laurent believe that these peaks are just the upper part of a much larger and more complex system. The two are out to prove a revolutionary hypothesis which could explain why the Himalayan range is so impressive. But to do this, they have to travel over 100 kilometers and get to the base of the mountains. Rivers can often help geologists. They expose rock formations that are usually buried in the ground. Kyle and Laurent's theory is that some rocks were superheated under the mountains. Granite, which is now found on the surface.
Oh, wow. This really is quite spectacular.
Look at these big garnets right there. Clearly this rock has melted.
What we can see here is we have these big garnet crystals right within this granitic melt. When we see garnet like this in the granites, it means that the granite itself formed deep within the earth, maybe 25 kilometers below the surface.
These rocks are nothing at all like the folded sedimentary rocks found high up in the mountains. These have been transformed in the deep substrata of the Himalayas. They are called metamorphic rocks. But it remains to be discovered by what strange mechanism they were able to travel 25 kilometers up from the depths of the earth.
What happens when we thicken the crust is we actually push rocks that were at cooler temperatures down deeper into the earth into hotter temperatures. When they're down there with all this heat and pressure, they start to melt, they form granites, and it really changes how the rocks react. They don't fold anymore like we see here. They start to flow, actually, almost like a fluid, kind of like silly putty.
Our researchers wonder about the proportion of metamorphic rock versus sedimentary rock in the makeup of the Himalayas.
This is great. This outcrop is absolutely spectacular. On the left, there's metamorphic rock, the granite, while on the right, it's all sedimentary rock. And in between, right here in the canyon in front of me, we have one of the major fault lines of the Himalayas. It clearly separates the two types of rock.
The hill to the left is made up entirely of metamorphic granite. And if you took away the vegetation, you'd see that this layer of granite lies beneath the sedimentary rock. It extends all along a major fault that separates the two sets of rock. This granite, softened by intense underground heat, is expelled along the fault. The immense weight of the Himalayas pushes the granite out like toothpaste from a tube. Kyle and Laurent are now convinced that much of the Himalayas are composed of metamorphic rock, which partly explains why these mountains are so high and why they continue to rise by a few centimeters a year. The Himalayas are so big that they actually create the region's climate. During the summer, the mountains trap the warm and humid winds from the southeast and then release the humidity as the torrential rains known as the monsoon. The rains have worn away large parts of the mountains and carried off sediments. Glaciers have eroded the peaks. Bit by bit, the Himalayas are taking a great journey to the south. The first part of this migration takes place here in the Siwalik Hills. This 2,000-kilometer-long range forms the southern flank of the Himalayas. In a dry riverbed 100 kilometers south of the Himalayas, Nepalese researcher Ananta Gajarel has measured the extent of this phenomenon.
These stones and pebbles were carried here by ancient glaciers all the way from the Himalayas. The more they're eroded, the smaller and finer they become. We can see some over there that are quite fine. This cliff is entirely made of Himalayan sediment. It arrived here 6 or 7 million years ago. Eventually, all the sediment will be carried all the way to the Bay of Bengal.
Most of the sediment of the Siwalik Hills will eventually take a trip of over 3,000 kilometers, carried by two great rivers, the Ganges and the Brahmaputra. This process has been going on for at least 20 million years. Enormous quantities of Himalayan sediment have been funneled into a trap between India and Burma. The land formed no more than 30 million years ago, making Bangladesh the last piece of the Asian continent as we know it today. The entire country sits on a gigantic sandbox. It's an unstable region whose future is uncertain, largely made up of streams and rivers, marshland, and ever-shifting shorelines. The entire southern part of the country would literally disappear if it weren't for a constant supply of sediments washed down from the Himalayas. Sedimentologist Christian-Franz Lenoir is trying to predict the geological future of this precarious region.
We are right above the confluence of the Ganges and the Brahmaputra. During this season, the flow of sediment is considerable. About 1 billion tons of sediment pass through here every year. 1 billion tons is hard to visualize on a human scale. If it were loaded onto trucks, the convoy would stretch as far as the moon and halfway back. So we're talking about an absolutely inconceivable amount of matter.
The lives of the people of Bangladesh are deeply connected to this sand, which they use for building. But that's not all. It's the constant flow of sediment that maintains an equilibrium, keeping the country just above the waterline.
One reason for this work is to be able to understand the mechanisms that bring sediment to this region. The south of the delta tends to sink below sea level. So there's a battle here between the sea level, which can rise a little bit, and the supply of sediment, a critical battle for the very existence of this entire zone and for the stability of these lands.
Christian and his team are measuring the capacity of the country to keep hold of the precious sediments that are brought by the great rivers. This sand might be able to give a glimpse into the future of an entire region. Christian's team starts by measuring the speed of the current.
Okay, the data's starting to come in. The water is 10 meters deep.
But the most important thing is to know how much sediment is suspended in the water. This tool takes a water sample at a precise depth. It gives the researchers an accurate figure for the amount of sediment per liter of water.
This is sand that we sampled at a depth of 11 meters.
Scientists believe that lighter sediments do not settle near Bangladesh, but are carried off by currents. Christian wants to know how far they travel. In order to study the final destination of the Himalayan sediments, a research ship, the Joy des Resolution, sails into the Indian Ocean, 2,000 kilometers south of Bangladesh. Here, deep drilling will provide Christian with precious core samples that may contain Himalayan sediments. To understand just how far the sediments have traveled, the researchers have collected samples all across the path of the major rivers. At the National Research Institute in northeastern France, Christian's team is about to compare 3 samples. The first was taken in Nepal, right on the slopes of the Himalayas. The second in the interior of Bangladesh, and the third is from the bottom of the Bay of Bengal. Researchers believe they are on the verge of an important discovery.
There are still a lot of very fine particles.
Their analysis reveals that the sediments from the Bay of Bengal are in fact completely identical to those taken in the Himalayan